Welcome to Unit 12, Differential Equations. So this one, 12.1, we're going to introduce differential equations. Differential equations are not a huge part of the AP test, it's about 10%, but it's really useful for future classes. If anyone wants to go into most engineering fields or any field in the physical sciences, uh, you're going to need differential equations. And uh, if I mean, the, I think it's important for students at BADA because there are some fields like if you want to be a lawyer, um, and you are an ESL 1 student, it's challenging because to be a lawyer, you really need to be proficient in English. And if you're an ESL 1 student, that means that you're still learning English, you're still getting better at it. There's a lot of English you have to learn to get better at to become a proficient lawyer. But there are a lot of fields in science and engineering that do not require as much English. They require more math. But if you're in taking this class, you already know quite a bit of math already. So you really should consider those fields if you're interested. They tend to pay well. The jobs are available. So if you enjoy math and science, you should consider pursuing studying science or engineering in college. Okay? All right. So, differential equations. How are they different from regular equations? Here's a regular equation, 3y plus 4 equals 19. What does that mean? That means 3 times y, then plus 4 gives us 19, right? To solve this, well, subtract 4 from both sides, and then divide by 3 from both sides, get y equals 5. So the solution is a number, or a bunch of numbers. The solution to equations are numbers. We want to check that this is true. To verify the solution, well, y equals 5 is true because 3y plus 4 equals 19. I plug in y equals 5. I get 15 plus 4 equals 19. This is true. So that's why y equals 5 is a solution to the equation. Differential equations are different. Here's a really simple one. 3y prime plus 4 equals 19. Another way to write this could be 3 dy over dx, because that's just the derivative. Oh, let me write this better. 3 times dy over dx plus 4 equals 19. So there's the differential equation. What does that mean? That means that 3 times the derivative of y, then plus 4 gives us 19. Okay. To solve this, well, we subtract 4, divide 3 on both sides. That's the same, and we get y prime equals 5. In other words, dy over dx equals 5. How do we solve this? One way we can solve this is the same thing as saying dy is equal to 5 dx. I integrate both sides. I take the integral of both sides. And what do we get? We get y is equal to 5x plus c. That's our solution. Notice that the solution is a function or a family of functions. That means that there are lots of different functions that work. Could be y equals 5x plus 1, y equals 5x plus 2, y equals 5x plus c, y equals 5x plus 0. They all work. C can be any constant. Okay. Let's verify that this is true. Okay. Well, 3 Well, if y equals 5x plus c, first we take the derivative. That means that y prime must equal 5. The derivative of 5x plus c is 5. So 3y prime plus 4 equals 19. 3 times 5 plus 4 equals 19. Again, so the solution is verified. Y equals 5x plus c is a solution to our differential equation. But that's not a number. That's a bunch of different functions. You might say, hey, this looks like an equation, not a function. Well, we could just write the function as f of x equals 5x plus c. There you go. There's our function. Okay. Now, not every differential equation is easy to solve. In fact, a lot of differential equations are not even solvable. Like, the one we saw is really just y prime equals 5. Anytime y prime equals a constant, it's easy to solve. We know how to solve it because we know what the solution should look like. We can we can integrate both sides. But most of the time, differential equations are hard to solve. If you're an engineering major, you'll probably have to take a class or two just on solving different types of differential equations. For the AP test, you're not going to be expected to solve a lot of differential equations. Just really some of the simplest ones that we will learn later. However, you should be if they give you the solution, they give you the answer, you need to know how to verify that the solution is true. So here's an example. The second derivative of y prime prime minus y prime plus 1 equals 0. Y prime prime minus y prime plus 1 equals 0. Again, we can just go with alpha. It solves differential equations, the ones that are solvable anyway. Y double prime minus y prime plus 1 equals 0. There we go. Differential equation solutions, that's right here. So there's a solution. We have y equals c1. This just means the first constant, because we have two different constants here. Just any constant. Could be 0, 1, 2, 2.5, and so forth. E to the x power plus c2, another constant, plus x. So for example, 3e to the x plus 2 plus x, or 5e to the x plus 10 plus x, those should all work. That's what Wolfram alpha tells us is the solution to our differential equation. Let's verify. Let's show that it actually works. That's a solution. Well, our differential equation has y prime and y double prime in it, so we have to figure those out. All right. Let's give ourselves more space. So, given that y is equal to c1 e to the x plus c2 plus x, okay, that means that, let's remove the space again. Okay, this just gives us more space. That means that the derivative, let's take the derivative of y. The derivative of e to the x is just e to the x. So the derivative of c1 e to the x is just c1 e to the x. The derivative of c2 is a constant, so we get nothing. The derivative of x is just 1. So y prime equals c1 e to the x plus 1. Next, y double prime has to equal to c1 e to the x. The derivative of 1 is nothing, so that's it. That's the second derivative. Now we can plug this into our differential equation. Y double prime is c1 e to the x minus y prime, which is c1 e to the x plus 1, and then plus 1 from our equation equals 0. We end up with the 2c1e to the x's cancel. The negative distributes, so I end up with negative 1 plus 1 equals 0. So 0 equals 0. That, of course, is always true. So we have verified our solution. Okay. So we know y equals c1 e to the x plus c2 plus x is a solution to our differential equation. Okay. So to verify solutions, we take these steps. Step 1, take any derivatives that you need. Step 2, plug in. Step 3, check to see if it always works. A couple more examples. Example 1. Y prime equals 4y minus 3. They're telling us the solution is y equals c1 e to the 4x plus 3 over 4. We want to verify that that is the solution. Alright, so let's do that. If y is c1 e to the 4x plus 3/4, y prime would be 4 times c1 e to the 4x because of the chain rule. The derivative of 3/4 is 0. Okay. So y double prime, we don't need to do y double prime here. Why? Because our equation doesn't have a second derivative in it. So we're set. We're ready to plug in. So y prime, that gives us 4 c1 e to the 4x is equal to 4y. What is y? Well, y is this one. Is c1 e to the 4x plus 3/4 minus 3. Okay. This gives us 4 c1 e to the 4x equals 4 c1 e to the 4x plus 3 minus 3. I can subtract the exponential term from each side. And once again, we get 0 equals 0. And that's always true. So that, in fact, is a solution. Okay. So differential equations are useful in a lot of places. Here's an example. Here's a real-life application, Hooke's law. So here's an example of a spring. Here's a simulation. We take a mass, put it on here, and we know the spring is going to move up and down, right? If the spring, if we take a first spring and if it's not very stiff, then we know that it's going to go up and down a lot. If we take a second spring, make it very stiff, that's the first spring. If we take the second spring, and if we make it very stiff, let's try this again. And make the second spring very stiff, and we know it's going to go up and down like this. Okay. The stiffness of the spring we call K, and we know that delta x, or x here, is just how much we go up or down or left and right. We know from physics that the force that we use, how much we pull, is equal to negative times kx. K is how stiff the spring is. So we know stiff, not as stiff, stiff, not as stiff, stiff. Okay. Now, F equals negative kx is actually a differential equation. Why? Because F is really just ma from Newton's second law, mass times acceleration. And acceleration is the second derivative of x. So we know that F is really ma, and a is x double prime. So really what we have here is a differential equation, m x double prime equals negative kx. This is an important equation. When we solve it, one of the solutions looks like this. X equals sine of the square root of k over m times t. Okay. Let's verify that this is in fact a solution of m x double prime equals negative kx. we have the first and we have the second derivative here. So we have to find the derivative and the second derivative. So if x is sine of square root of k over mt, then x prime has to equal the derivative of sine is cosine, but we have to pull out a square root of k over m by the chain rule. Okay. So the second derivative, x double prime, the derivative of cosine is negative sine, so we have negative sine square over k over m t. We have the square root of k over m from before. We have another square root of k over m from the chain rule. Multiply two square roots, the square roots cancel. So x double prime would be negative k over m times sine of square root of k over m t. Okay. Now that we have taken the derivatives, we are ready to plug back in. So we have m times our second derivative, negative k over m sine of square root of k over m t is equal to negative k times our x. X is sine of square root of k over m t. Okay. The two m's here cancel. The two negatives cancel. The two k's cancel. And these signs cancel. So really, this is just 1 equals 1, which is, of course, always true. So yeah, that's one of the solutions. Does that make sense, that the motion looks like sine? The answer is absolutely. What does sine look like? Sine x looks like this, right? This is related to the motion of the spring. In this video, we see that when the spring moves, when we track the position of the spring, it looks like a sine or a cosine. Right here. So let's see. When we track the position of our box, we end up with this graph, which looks just like a sine or a cosine. And we solved this mathematically using differential equations. We got that given our description of the motion, we found that the solution is actually look like a sine. So there we go. We have figured out why the spring moves like sine x. Okay. So summary, what did we learn? Differential equations are just equations with derivatives in them. Solutions to differential equations are not numbers, but families of functions, like f of x is equal to c1e to the 2x plus cosine x plus c to 2. Again, on the AP test, you're only expected to solve a few differential equations. The ones that you should know how to solve, we will learn later in this unit. But you should know how to verify, check that a solution is true. How do we do that? Well, step 1, take the derivatives that you need. Step 2, plug into the differential equation. Step 3, check to see if it's true. Okay. That's it.